Hello and welcome back everyone. This is a selection of tooling for the mill. I would like to make some more, but getting concentricity between the taper and the tooling features is more difficult than you might think. Machining all the attributes between centers is the best way for perfect alignment of all the features with the taper. But if, like this side lock holder, the tooling features are internal or a hole, then turning that concentric with the taper can be a challenge. So I made a tool for that. It's a chuck for the lathe and it has an NT40 taper. It also has a power drawbar, and that also means it has power eject. If you have a mill and plan to make some tooling for it, there may be some takeaways in this video for you. This project, as most do, starts with a concept drawing. The idea I have is to make a hub that bolts onto a back plate which in turn mounts to the spindle. It could be any size spindle, mine just happens to be a D8. The front of the flange is 150mm in diameter and the body will be turned down to 75. This will fit into the low spindle bore, which is 80mm. The hub incorporates an NT40 taper to suit my mill, but this could easily be NT30, NT50, R8 or any other taper to suit your mill. The front face will have two 16mm square drive dogs to engage with the tooling and transmit the drive, as will be the case in the mill. The rear of the body will have a captured M16 socket head cap screw which will become the drawbar. The head will need to be sleeved to properly engage with two thrust bearings, one on the inside and one on the outside of the drawbar head. I plan to make a press fit sleeve that will be welded to the cap screw. There will be a drawbar cap that is bolted to the body by 8 M8 cap screws. This will enclose the drawbar head and allow it to be reversed to eject tooling from the taper. To operate the drawbar, I will need an extension that will fit through the lathe spindle and can be activated from the outboard end of the headstock. This extension will be removed when the lathe is in use. Although not shown on the plan, the hub will be mounted onto a modified faceplate, the same as I did for the ER40 and 5C collet chuck builds. The drawbar is also not shown on this plan. Well, that's the theory, and as always, the plans are subject to change as the project progresses. For the hub, I'll start with a length of 50mm 1045 bar stock. A quick check, and this weighs in at 23 kilos. I'll set this up on a 4-jaw and roughly centre it. I can now face the end and true up the edge so I can turn it round and gain the access I need to reduce the diameter of the body. I'm running a TNGG insert and there's a lot of swarf to contend with, so I bought a chip screen from the mill. This is an opportunity to try out the spray coolant system I built a little while ago. It's running around 7 psi and it's working very well. I made another chip screen out of an offcut of Perspex and a spare mounting angle plate. It fits nicely on the saddle. These angle plates are 3D printed and have 9 8mm magnets to hold it to the lathe or mill. It also has a 16mm hole to bolt it to the mill table if needed. They measure 100 by 75 by 75. I made a variety of sizes and shapes of these screens, mostly for use on the mill. I'll use a shop vac to clean up the mess. If you're a regular viewer, you'll know that I'm not a fan of compressed air, as all that does is relocate the swarf to a wider area. Now the body is to size, the next step is to machine the pocket for the drawbar head and inside thrust bearing. The blue face is a finished machine reference face, and this will mate with the camlock plate. The red face is a temporary reference face that will be used to line up the part for further machining. It will later be turned to become a permanent reference surface. I'll drill a 14mm hole, which is the root diameter for the M16 drawbar thread. I'll need this hole to go full depth so I can use it to bolt the hub onto the mill table. The pocket will be 30.5mm wide to take the thrust bearing and allow for a little rattle room for the increased diameter of the drawbar head. Yep, that's fine, I'm happy with that. Next I'll tap the hole with an M16 spiral tap. The threads only need to go to a depth of 12 to 15mm, as there will be an internal feature of a 25.4mm clearance hole to take the tail of NT tooling and provide a space for the tool to be rattled into place without bottoming out on the hub. I can now remove the hub from the chuck, turn it round and mount it in the 3-jaw. I'll protect the body from the jaws with a piece of card, and I'll check the alignment with a dial gauge against the temporary reference surface. The chuck that came with this lathe is very accurate. Some light taps of the machinist hammer soft face and it's good to go. This is a surface cut that I can have as a reference surface for mounting in the mill later. The final finishing cuts will be made when the hub is mounted into the camlock plate. The next part is to machine the drawbar cap. This is made from a length of 4140, as it's the only material I have on hand that's 80mm in diameter. It has the same 30.5mm pocket as the hub, and it has a 16mm through hole to take the drawbar extension. I cut the cap off on the bandsaw and then remounted it in the forge to face off the outside end. A test fit with an Allen socket and it looks fine. Now for the mill. I'll set the cap up on a piece of sacrificial aluminium so I can drill through the cap without damage. I have the grey ring light that I made in a previous video installed, and it has a clear lens. This is its first practical use. Now I have some chip control in place, I'll centre the spindle, then set the DRO to circular mode. It's asking for the radius, which will be 26.5mm. The start and finish angles will be 0 and there will be 8 holes. The direction will be clockwise, which is represented by the number 1. I'll first spot the holes in an 8mm spot drill. Next I can drill the holes. I'm drilling these through into the aluminium. The holes are then counterbored, and using an end mill I'll flatten the bottom of the counterbores and finish them off with a countersink. This part is now complete. recentered the DRO and used the same settings as I used previously for the cap to spot, drill and tap the 8mm threads to attach the end cap. Turning the hub over, I can now drill and counterbore the 6 11mm holes to attach the hub to the camlock plate. It's also sitting on pieces of sacrificial aluminium. The PCD for these holes will be 120mm, all other settings are the same as before. As this will be a Set-Tru mounting, I'll make the holes 11mm to allow some wriggle room during assembly. Again, I'll use an end mill to flatten the bottom of the countersink so that the cap screws can't tie to self-centre when the hub is being aligned. I'll give the holes a substantial countersink as these surfaces will be recut after assembly. A long series countersink bed in the draw press removes the burrs on the back face. Primary machining of the hub is now complete. The heads of the cap screws are 16mm in diameter. I'll turn these down to about 14mm to allow for movement when using the Set-Tru adjustment. This VCMT insert works well in a confined area, but this insert looks and sounds a bit dull. Bugger, that's taken the end off it. Oh well, just turn it round and move on, I suppose. These inserts are good at what they do, but they're a bit fragile. That being said, the socketed cap screws are 12.8 hardness rather than 8.8, which is what you normally see in a high tensile bolt. The new edge feels a lot better and you can see the difference. The first couple of screws will need a clean up. Yep, that's enough wiggle room for the adjustment. Now to convert a perfectly good faceplate into a mounting plate. I modified one of these faceplates to make it usable as a faceplate. I cleaned up the slots and extended 6 of them between the camlock studs, and now I can mount workpieces on it with ease. This other faceplate is the last remaining spare I have after the ER40 and 5C collet chuck projects. As I did in previous projects, I'll separate the outer ring from the centre. I'll set it up on a spigot on the mill table to hold the faceplate in one place. This will allow it to be unclamped and rotated without it moving on the table. I have the blue ring light set up, which has a slight diffusing of the light compared to the grey light. This also is its first use. I'll centre the DRO so I can use the same setup later in the project. Using a 16mm solid carbide end mill, I'll cut the plates between the slots. I have the vacuum set up to remove the fines and dust. Most of the heavier swarf will just drop to the table, but containing the finer particles is important. I don't want iron dust floating in the air. I'm super impressed with this light ring. The illumination is just great. I got to the final cut, then this happened. I did leave several tabs on the bottom of some of the cuts to support the core and not drop when the last cut was made. Apparently they were not strong enough to support the plate and it broke free. The core just dropped and it was constrained by the spigot, so no harm was done. Now I have 3 of these outer faceplate rings. I'd like to find a use for them if I could. If you have any ideas, please let me know in the comments. Now it's back to the lathe to clean up the outer edge and get it level. This will provide a clean surface of consistent diameter that I can then set up in the mill. The vacuum did a good job of containing the swarf. Not much landed on the bed covers. Now to cut the scallops. This DRO requests the diameter, not the radius, as the other DRO does. For this setup, the diameter will be 235mm and there will be 36 scallops. That's 1 for each slot with 2 in between. I'm using the same 16mm carbide end mill to plunge the scallops and rough them out. I'll then follow with another circuit using a 20mm high-speed steel end mill to bring them to final size and finish. I have the depth stop set to ensure that plunges are consistent. You've seen me do this before, so no need to dwell on this part of the project. I covered this process in detail in a previous video for the ER40 chuck build. I'll leave links to that at the end of the video. Back on the lathe, I'll clean up the ends and remove enough until I'm happy with the look and feel of the scallops and the flats between them. I'm using a high-speed steel tool bit as the carbide inserts are not fond of interrupted cuts, and I've already broken one insert today. The chamfer on the front edge and a rounding on the back finishes the edge. Now I'll face off the plate, as is normal practice for all faceplates, to ensure that the plate is running true to the lathe it will be used on. Next, I'll increase the bore from 65 to 77mm. This allows the 75mm hub to fit and still have some wriggle room. The shop vac doesn't seem to be doing much. After filming, I've found that the hose had a kink in it. Great. Now that's done, I can machine the relief for the hub. This will be 140mm in diameter and 11.5mm deep. I did plan on having this 150mm in diameter, but when I realised that that would interfere with the threads for the camlock studs, I made a change. To overcome this, I relieved the back of the plate to 138mm and 12mm deep, which you can see in the plans. I think this is a good compromise. It's back to the mill to drill and tap 6 and 10 holes for the mounting screws. The pitch circle diameter is 120mm. As this will be a Set-Tru chuck, I'll drill 4 5mm through holes at 90° spacing from the centre of the scallops to the inside of the relief. They will be tapped M6 to accept some long series grub screws. For the Set-Tru pins, I'll turn down some 6mm brass rod as I don't have any 5mm material on hand. I'll just cut them off with a junior saw as that seems easier than parting them off. The Colchester has a taper turning attachment, but I don't have one on the Toolmaster. To set the taper on the compound, I'll dial it in against an arbor. Using the ER40 collet chuck I made in another project, I'll set up a 22mm arbor and hold it in place with a tailstock. I know that this chuck is accurate, and I'm assuming that the arbor is both accurate and concentric. Well, you know what they say about assumptions, don't you? More about that later. In the meantime, I'll dial it in, getting as close as I can. Mostly when cutting taper, some fine adjustments will be needed along the way, as it's rare to get a perfect alignment straight off the bat. Now I can assemble the hub to the plate. After a good blowdown and clean, the pins are inserted and checked for movement with the grub screws. I made sure that there were not any burrs or dust present that might cause issues. The plate is inserted and the cap screws fitted. I'll leave them a little loose so that the Set-Tru adjustments can be made as the hub is dialed in. I 3D printed a couple of protector caps from TPU95. These will prevent the hub from contacting the spindle taper during fitting and removal. The spindle taper and nose are the most valuable reference surfaces on the lathe and must be protected at all costs. The cap with the hole will be a permanent attachment later after the drawbar cap is assembled. I've made a witness mark on the chuck so I can mount it in the same orientation every time I want to use it. I can now dial in the Set-Tru and lock the cap screws. The face I'm using to set the alignment is part of the temporary reference face and will remove any balancing issues that may occur due to the mass of the hub. After I've tightened the cap screws, I'll reface the surface along with all the other faces of the chuck so that everything is concentric with the taper. The next step is to bore the relief for the tooling shank. This is 25.4mm in diameter and is 35mm deeper than the length of the taper. This will accommodate both the length of the tooling and allow for pull-up room meaning the drawbar won't bottom the shank of the tooling into the back of the hub when it's activated. Now that's done, I can start cutting the taper. I'm using a 20mm left-hand boring bar with the lathe running in reverse. This has two benefits. Firstly, I get a better view of the taper as the boring bar starts its cut, and secondly, I can use the same compound slide setting to machine the mill taper on any mill tooling I want to make in future projects. I'm manually feeding the cross slide, and the taper was relatively quick to cut. However, I did need to make two fine adjustments to the angle along the way. A final blue test and I'm happy with the result. Well, the chuck comes off the lathe again and goes back to the mill table. Lots of chuck changes in this project. Using a 12mm high-speed steel end mill, I'll machine the 16mm slots for the drive dogs. I'm using the spray coolant again and I'm impressed with its performance. I think I prefer this to flood coolant. This is the first project that I've used these ring lights. I'm not sure which one I prefer, but they both make a massive difference to the lighting solution. This operation is complete with the two tapped 6mm holes to attach the dogs. Yep, that's fine. I'll cut the drive dogs from a piece of key steel and I'll counterbore them to accept the mounting screws. I'll machine them to final size when they're fitted to the chuck so that there are no rough edges exposed. I'll also blacken them. Now for the drawbar. This is an M16 by 2mm socket head cap screw. I need to waste the screw about 12mm to clear the rear threads and the back face of the hub. This allows the drawbar to rotate freely to engage and pull back the tooling while still being captured by the back of the hub. The cap screw head is not wide enough to fully engage with the thrust bearings, so I'll machine a ring to increase its diameter. I'll make it an interference fit on the cap. I'll machine it to 30mm outside diameter, which will provide the required clearance inside the pocket. I'll make 2 drawbars as it just makes sense to do that. The press makes short work of pushing the ring into place. Not much pressure is needed. This is a light interference fit. I don't want to create any internal stresses in the ring. Now I'll TIG weld the ring to the cap screw to secure it. I'm working on a better way of filming welding, so I hope to have an improvement in welding footage in future videos. Well, that's an improvement on my previous welding efforts. The result looks pleasing enough and I'm happy with that. I'll face them off and skim them to ensure they're concentric with the thread. Now for the drawbar extension. I'm machining this from a length of 41/40 as it will be subject to some stress. After facing it, I'll machine the ends to 16mm. I'll then put in a collet block to mill 6 flats to fit a 14mm impact socket at the drive end. After cutting the bar to length, I'll repeat this on the other end to fit the drawbar. The extension will fit through the spindle and be activated by a small electric socket wrench. I'll need to make 2 plastic rings to centre the extension inside the spindle and make engagement in the back of the chuck easy. To restrain the rings, I'll cut some grooves and add circlips to prevent them from walking down the bar. The ER40 collet chuck is getting a bit of a workout today. I'll harden both ends of the extension so they will hold up better in use. Well, not really harden, but just a tougher hex will be fine. I'll heat the ends and quench in canola oil. Lastly, I'll weld a socket into the end of the extension bar. Now that's done, I can make the rings. I'm using a piece of acetal bar, and this is really nice stuff to turn. It's 80mm in diameter, and I'll machine the rings down to 78mm, which should provide sufficient clearance inside the spindle while still allowing free movement to engage with the chuck drawbar. I'll bore a 20mm hole to make a free fit on the extension, and I'll part them off 20mm thick. Assembling the extension, the circlips will be fitted sharp side out, which is normal practice. A drop of oil and they run freely. I did go back later and increase the chamfer as I wasn't happy with those short ones. Now to assemble the chuck. The internal thrust bearing is the first item. The thin thrust washer goes in first as it will be supported by the part with the biggest and most stable mass. The bearing gets a light coat of grease, then the thick thrust washer as this will endure the rotation and pressure of the drawbar. The drawbar is next, and it's wound right through the capture threads, making it free to rotate. The outside thrust bearings are assembled into the cap the same as before, with the thick thrust washer installed last against the drawbar. The cap can now be installed and the cap screws tightened. Now to try it out, I'll insert a collar chuck and use an electric wrench to tighten it. It works really well. Now the chuck is fully assembled, I can mount on the spindle and try it out. I've fitted a protection cap to protect the spindle taper. This will remain in place permanently. I'll check the accuracy of the taper with a MeasureMax 100th indicator. The needle shows barely a flicker. The micron indicator also shows barely a flicker and less than a micron. I'm still not convinced by this indicator, but you can make up your own mind. It does look to be in the range I would expect given the results of previous builds. It's also worth noting that the chuck has been removed and reinstalled several times since the taper was cut, so what you're seeing is repeatability in action. The drawbar extension goes through the spindle to connect into the drawbar. The split view shows how it works. And because it has a power drawbar, it also has power eject. It goes without saying that the drawbar extension is removed from the spindle during use. I'll install the arbor I used to measure the taper and check the runout. I said earlier that I made some assumptions about its concentricity, and here's why. It's got a 1/10 of a millimeter runout. That runout contributed to the need for adjusting the compound slide as I was machining the taper. We just established the runout in the chuck taper, so this runout is in the arbor and not the chuck. This is a brand new arbor and it wasn't cheap. I'm unsure of the manufacturing tolerance for these arbors, but I'm sure it's less than this. Well, now I can make mill tooling that will be both accurate and concentric. I can also machine some taper blanks for future opportunities. This setup will also allow me to work on existing tooling a lot easier than mounting them between centers, as I did in a previous video. Well, this has been a big build and I'm very happy with the end result. There's been a lot on this project and several components to make. I'm sure someone will leave a comment on sacrificing a perfectly good faceplate, but I'm happy to put it to this use. If you're planning on making some tooling for your mill, this system will make that a whole lot easier. You could make this chuck to fit any lathe and any mill taper you might have. This chuck can also be modified for other tapers such as NT30, NT50, R8 or BT series tapers simply by making different hubs. The Set-Tru feature will make changing hubs a relatively simple task. Feel free to screenshot the plans and modifiers you might need if you would like to make one of these to suit your equipment. If you made it all the way to the end of this video and while watching, I'm very grateful, and as always, thank you for watching. Around 85% of my viewers are not subscribed to my channel. Imagine if half those people made the choice to subscribe, what that would do to the algorithm. My channel is not monetized and I don't have an AdSense account, so the algorithm tends to ignore my videos. I hope you liked this video, and if you did, please like the video. Be productive, be creative, but most importantly, be safe in your shed. I'll catch you next time.